Assalamu alaikum. Dear viewers, I am Dr. Noshin Afshan and you are watching the lecture of Inorganic Chemistry with the special topic of discussion being valence shell electron pair repulsion theory, that is also abbreviated as VSEPR theory. So, the main contents of the discussion are its introduction, postulates, and prediction of the geometry of a series of examples. So, the VSEPR theory was suggested by Sidgwick and Powell scientists in 1940, and later on it was developed by Guisi and Nihom in 1957. And they had postulated that the geometry of any molecule can be predicted if the central atom is determined. And along with the determination of the central atom, it is compulsory to understand the arrangement of the electron pairs, arrangement of the bond pairs, estimation of the bond angle, and drawing the structure of the molecule. So, on the basis of all these predictions, the geometry of a molecule can be estimated. So, in the next example, we will discuss that how we determine all these points and make them applicable for the determination or for the prediction of the geometry of any molecule. But before going into detail of the examples, we should understand the meaning of the basic terminologies that are central atom and ligand. So, what is the central atom in fact? It is any atom that is surrounded by a number of atoms. For example, generally in the system of AB4, the atom A would indicate a central atom, because here the central atom A has been surrounded by 4 B atoms, and specifically in the example of silicon tetrahydride, one silicon atom has been surrounded by 4 hydrogen atoms. So, in this case, the central atom silicon would be termed as central atom, while all the atoms that surround a central atom, like here there are the 4 hydrogen atoms, these would be termed as ligands. And generally in the system of AB4, the 4 B atoms would be ligands. Now, what is the valence shell electron pair repulsion theory? It may be stated as electron pairs consisting of both lone pairs and bond pairs that surround a central atom in such a way that there is minimum repulsion and maximum distance in between them. For example, the tetrahedral geometry of silicon tetrachloride or silicon tetrahydride. Because here in this case all the 4 ligands have been placed at the maximum distance from one and each other, and if the distance between them would be maximum, then automatically there would be minimum repulsion. So, assuming this type of geometry, that is tetrahedron, the bond angle would be 109 degrees, and that assumes that it obeys the VSEPR theory concept. Now, we move towards its postulate. The first postulate is the lone pair of electrons occupies more space as compared to the bond pairs, and the order for the interaction between lone pairs and bond pairs comes out to be the lone pair interaction, or in other words, the interaction between two lone pair of electrons would be maximum, and then the interaction or repulsion between lone pair and bond pairs would be less than lone pair interaction. And in other words, we may say that the lone pair interaction would occupy more space as compared to lone pair bond pair interaction, and that would occupy more space as compared to bond pair interaction. For example, in the case of in the case of triangular geometry of selenium dichloride, where one lone pair surrounds more space than any of the two bond pairs. So here, the first postulate in fact tells us the information about the space that has been occupied by a lone pair as compared to that of the bond pair. So, one lone pair of the electrons would occupy more space as compared to the space that is occupied by one bond pair. And similarly, if there are more than one lone pair and also more than one bond pair present around a central atom, then the lone pair interaction would occupy more space as compared to lone pair bond pair interaction, and that would occupy more space as compared to bond pair interaction. Then the next point indicates that the multiple bonds that are double or triple bonds would occupy more space as compared to single bonds. But the main point is multiple bond will be considered as a single bond. So the correct order of the space that is occupied turns out to be the triple bond occupies more space as compared to the double bond, and that would occupy more space as compared to the single bond. So the next postulate is repulsion between electron pairs varies inversely with the value of the bond angle. For example, in the case of AB2 system, that is here, where the bond angle is 180 degree, when the geometry becomes triangular, in this case that is AB3 system, the bond angle comes to be 120 degree. So if you compare these two examples, then the value of the bond angle decreases from 180 degree to 120 degree. And according to this postulate, the repulsion between electron pairs varies inversely with the value of the bond angle. That means if the value of the bond angle would decrease, repulsion between electron pairs would increase. Because here the value of the bond angle is the maximum, that is 180 degree, and the repulsion is minimum between these two electron pairs. But in the case of AB3 system, value of the bond angle is lesser than the 180 degree, and that is 120 degree. So the repulsion would be slightly greater than the repulsion between these two bond pairs in the case of AB2 system. So in this system, AB3 system, the repulsion between electron pairs would be slightly higher than that in the case of AB2 system. And moving towards the tetrahedron, that is AB4 system, value of the bond angle still decreases from this 120 degree up to 109.5 degrees. As the value of the bond angle decreases here, so the repulsion would be greater. The next postulate states that with the increasing value of the electronegativity of any atom, its influence on other bond pairs would decrease. So in other words, the value of the electronegativity is in inverse relationship with the influence on other bond pairs of electrons. Because any atom has also its influence on the other bond pairs. So, the value of the electronegativity of that atom would be in inverse relationship with its influence on the other bond pairs of electrons. Because the highly electronegative atom would attract the lone pair of electrons or the bond pairs of electrons with the higher strength as compared to that of lower value of electronegativity. For example, the tendency of fluorine to attract any electron pair would be higher as compared to the tendency of the hydrogen atom. And the next postulate states that the lone pair creates some distortion in the geometry of the molecule that is determined from the value of the bond angle. So, if you determine experimentally the value of the bond angle, you may easily determine its geometry. And in turn, the distortion in that molecule as well.